Hello and welcome. In this video, we're going to talk about lines and postulates related to lines and planes. Our objectives are that we can define and apply congruence for statements, understand the notation for congruency versus length, that we can explain and apply the ruler postulate and the segment addition postulate, and that we can just identify and use postulates in general. So let's go ahead and jump in. Let's start with some vocabulary. So one of our objectives in this section is to look at postulates that involve lines. So we should probably start by defining what a postulate is. A postulate is a rule that's accepted without proof. So it's sort of going to feel a bit like a definition or something that is maybe obviously true, but it is something that we're going to use to be able to prove theorems and other more complex things further on in the class. Our next vocabulary word is congruent segments. Two segments are congruent segments. And the symbol for congruency is here. Two segments are congruent segments if they have the same length. So we would say that lengths are equal. 7 equals 7. We would say segments are congruent. The length of AB or the segment AB is congruent to the segment CD. So if we're talking about length as a number, we're using the equal sign. If we're talking about length in terms of comparing two segment lengths, we would say that it is congruent. And in order for two things to be equal or to be congruent, we need to talk about distance, the distance between points A and B, which we could just write as AB without the segment symbol above it. So this is indicating length as it does up here, is the absolute value of the difference in the coordinates from A to B. So really it's just how far is it from A to B. And we may be looking at how far it is from A to B in a coordinate plane. So we might be looking from like one side of the axis to the other, or we might just be looking at a specific segment, but the distance is the length between the 2 points. So now we're going to get into these postulates that we're learning in this section. The first is the ruler postulate. The ruler postulate says that points on a line can be matched with real numbers. So if we have in a coordinate plane, if we have like the coordinate 2, 5 and the coordinate 2, 8, we could use those to find the total length or the distance between points A and B. The reason this is called the ruler postulate is because in theory we could actually use a ruler to measure length. So we're saying no matter where we're looking at this segment, whether it be abstract or in a coordinate plane, we could find its length using a ruler, or we could find its length using something that matches us with numbers and length. The 2-point postulate, which we actually identified this when we were first defining a line. Through any 2 points, we can draw exactly one line. So that is the 2-point postulate. Through any 2 points, we can draw exactly one line. And then the line point postulate says a line contains at least 2 points, which these two obviously go together, right? If I can draw 2 points to pass through a line, then a line must contain at least 2 points. And in theory, a line really contains an infinite number of points. And then the line intersection postulate says that if 2 lines intersect, they intersect at exactly 1 point. We spend a lot of time in Algebra 1 talking about what happens when 2 lines intersect, and we know that if they do intersect, it's just going to happen once. Okay, we have a few more postulates. Now that we talked about postulates having to do with lines, we're going to talk about their counterparts having to do with planes. We know that a plane is defined to be a flat surface, sort of like a wall or a piece of paper extending forever in all directions. And when we defined a plane, we talked about how every plane must contain at least 3 points. And that's what these two postulates are going to say. Through any 3 non-collinear points, there exists exactly one plane. And a plane contains at least 3 non-collinear points. And the reason that the word non-collinear is there is because if all 3 points were on the same line, that doesn't necessarily define a plane. That line could be in different planes. Next postulate, the plane line postulate, which says if 2 points lie in a plane, then the line containing them is also in the plane. 2 more, we're almost there. The plane intersection postulate says that if 2 planes intersect, their intersection is a line. And we talked about, for all of these postulates so far, we really talked about and visualized these in the first video where we talked about the definitions of planes and lines and intersections. Lastly, and probably the most important in this section, is the segment addition postulate. The segment addition postulate says that if we have a point that is between, and that word between means exactly what you think it means. Here's A and here's B, and Here's A and C, and B is lying in between them. If B is between A and C, then the length of AB plus the length of BC is equal to the length of AC. And this should make intuitive sense. If we break something into pieces and add the pieces together, we should get that full length. But the segment addition postulate is going to come into play quite a bit in future sections. Now that we have learned some postulates, let's try and identify them from pictures and look through some examples that involve them. Okay, I want you to look back at the list of the postulates and see if you can identify what each of these biconditional, because we have if and then statements, what each of these biconditional statements are expressing visually, and then write the name of the theorem underneath. So you should be looking back at that list and identifying which postulate is being demonstrated in this picture. All right, number 1 is demonstrating that if two lines cross or intersect, then they intersect at a point, and that postulate is called the line intersection postulate. There we go. And number 2 has two planes intersecting, and then it looks like it's highlighting the fact that we have a line where that's happening. So if two planes intersect, then their intersection is a line. That is the plane intersection postulate. Let's look at another visual. Okay, now we're going to look at a visual, and from that visual, we're going to identify key components using two of these postulates. So here we have two planes, they are crossing. There are some points and lines happening. Number 3 is asking us to use the plane point postulate. So if you look up at your notes, the point plane postulate says a plane contains at least 3 non-collinear points. So let's look at a plane. Let's look at plane P. So I can see here this plane is identified to be plane P. And let's go ahead and identify 3 points that are not collinear, that are not on the same line in this plane. So I can see point B, point A, and point C all lie within plane P. Okay, number 4, the plane line postulate says if 2 points lie in a plane, then the line containing them lies in a plane. So I want you to identify a line, 2 points on the line, and what that plane is that they lie in, and go ahead and write a statement similar to what we did on number 3. So points A and B form the line AB, which lies in the plane P. Lies in the plane P. All right, let's look at some different types of examples where we're using the postulates but in a more mathematical way. All right, for these 2 examples, we're going to plot 2 segments, and then we're going to determine if the segments are congruent, meaning we're going to determine if the segments have the same length. So just as a reminder, when we are plotting points, we're given an x and a y value. The x value tells us left or right, so -3 is going to tell us that we're going to go to the left, 1, 2, 3, and +4 tells us we're going to go up 4, 1, 2, 3, 4, and I'm going to put a coordinate right here. Similarly, the point 2, 4, 1, 2, and then up 4, 1, 2, 3, 4. And then I'm going to connect those 2 points with a segment. And using the ruler postulate, I can actually determine the length here because I can count how many spaces it is to go from A to B. 1, 2, 3, 4, 5. So AB has a length of 5. And since I'm talking about the length numerically, I'm going to put a segment, or I'm not going to put a segment symbol, and I'm going to put an equal sign. Why don't you go ahead and plot LM and connect them and count to determine that length? All right, so L is over 1 up 3, and M is over 1 down 2. And this, if I count 1, 2, 3, 4, 5, also has a length of 5. So LM equals 5. And this question is asking us to determine if they're equal. So since AB is equal to LM, we can say that segment AB is congruent to segment LM. So here we're talking about length as a value, and here we're talking about segment congruency. I want you to go ahead and pause the video and work through number 6 on your own, and then unpause the video and see how you did. So here I have plotted my segments. AB has a length 1, 2, 3, 4, 5. And CD has a length 1, 2, 3, 4. And those are not equal. I said 4, but I wrote 5. Those are not equal, so I could say that AB is not congruent to CD. Let's look at a couple more examples. Okay, here on 7 and 8, we're going to look at the segment addition postulate. And I don't want you to just jump immediately into the addition or subtraction you may think is happening. What I really want you to do is to start with the statement that you can show using segment addition, and then plug in what you know into its key places using substitution, and then find the answer that you're being asked for. So here's what I mean by that. On number 7, we're being asked to find the length of DF, or to find the length of the segment. So DF is equal to, this whole piece is equal to DE plus EF. Now I'm going to plug in what I know. DF is the thing that I'm trying to find. DE, we can see from the original portion, is 23. And EF, we can see from the original picture, is 35. And if I combine those, I get DF, which is going to be 58. I encourage you to pause the video and try number 8 on your own. Make sure you're plugging the correct pieces into the correct places. And make sure that you're starting by writing the segment addition statement that allows you to do any of the work that follows. Then unpause the video and see how you did. So here's our segment addition setup. FH, the full length, is equal to FG plus GH, and we're trying to find GH. Now I can plug in what I know. 36 equals 21 plus GH. So to find GH, I need to subtract 36 minus 21, which is going to give me 15. Now, before we wrap up this video, let's look at 2 last visuals to really solidify in what we were covering with the postulates in this section. Okay, number 9 says, sketch a diagram showing the line TV intersecting the segment PQ at a point W, so that TV is congruent to WV. So the first thing I'm going to do is I'm going to draw a line. On this line, I'm going to label 2 points, T and V, because we're being asked to label 2 points. Now we're supposed to draw a segment that intersects the line in 2 ways. It intersects at point W, and it looks like W is breaking this piece of my segment in half. So I'm going to approximate where that is. I'm going to use the mathematical symbol of this little tick mark to indicate that those 2 segments are the same length. And then I'm going to go ahead and draw the segment, which is PQ, that's going to pass through W. And then I'm going to label the endpoints P and Q. All right, for our very last example in this section, I'm going to encourage you to pause the video, read through the statements A through E using the diagram on the right, and circle all that cannot be assumed based on the graph. So it's sort of like, can you determine that this must happen, or are we unsure whether or not it must happen? Then unpause the video and see how you did. Okay, for part A, it says points A, B, and F are collinear. A, B, and F. They are definitely all on that line. So since we're trying to circle things that cannot be assumed, this is definitely true. So I'm going to cross it off and not circle it because it can be assumed. B says points E, B, and D are collinear. E, B, and D. It looks like we could draw a line going through all of them, but since one is not written there, we cannot assume. So this cannot be determined. It might be true, it might not be true. Without a drawn line, we can't assume it to be true. For C, it says AB, the line, is perpendicular to plane S. Well, I do see a perpendicular symbol here, and this is plane S, so that is true, which means I'm not going to circle it. CD is perpendicular to plane T, so I can see that they're intersecting, but since I'm not sure how, this cannot be determined. And lastly, line AF intersects line BC at point B. So if, let's clear this up a little bit, I look at line AF and I look at line BC, they are crossing at point B, so this is true. And the only things that I cannot assume to be true are B and D. let's go ahead and wrap this video up. Okay, so 3.2 was about lines and postulates involving lines. In this lesson, we focused on what the postulates are, how to identify them, how to use them, giving a diagram, and specifically how to apply the ruler and segment addition postulates in order to find values of segments. So go ahead and write down any questions you have, and I look forward to supporting you on this. Thanks for listening.